Okay, now I want you to recall, and let's even write that down. Recall Rn that we did in a previous lecture. We talked about Rn, and we actually defined Rn there to be the set of n-tuples of real numbers. So we first defined, if I remember correctly, we first defined the notion of these n-tuples, and then we said Rn would be the set of all these n-tuples of real numbers, and we said we could do the same thing for, really for any set. We said take a set X, I think we did anyway, and if we didn't, well, we can say it now. This would be the set of all n-tuples where the xi is in capital X for every I. And so what we want to do now is we want to generalize this a little bit, because here all of the n-tuples are drawn from the same set R, the reals. Or over here, all the n-tuples are drawn from the same set capital X. So here we want to generalize that to allow for different sets so that the n-tuples, their different components could come from different sets. So what we'll do here then is we will say, let's make this a definition. For any two sets of numbers, sets of anything. We'll see an example just shortly. Well, in fact, I think we saw some examples last time where the sets here were not numbers. For sets X and Y, the Cartesian product, I guess I could have just said the Cartesian product of sets X and Y, is X cross Y. That's the notation we use for it. And here I've used a notation. I don't know if I used this before. I certainly don't think I've described or explained it before. This is a notation that's become common for meaning that the thing over here on the left is defined by this over here on the right, or is defined to be what's over on the right. So this is going to be the set of all pairs, and their ordered pairs. The order matters, as we saw before. The set of all ordered pairs such that X is in X and Y is in Y. And let's just remind ourselves, as we did up here, and of course here it's even more obvious that the order matters, because if I took YX, it has to be the second thing that's in Y. I suppose we could define it so we could flip them around, but that wouldn't really make a lot of sense. So let's recall from what we said earlier that the order matters, and in fact we capture that by often referring to these as ordered pairs, and repetition is okay. Well, here, I suppose repetition doesn't actually have any particular meaning if X and Y are different sets, so let me take that off. I think that's not very helpful. It's certainly okay if X equals Y, but it doesn't really make any sense, I think, if X and Y are different sets. So just say order matters here. And we can do the same thing for an arbitrary finite number of sets. We would say for sets capital X1 out to capital Xn, we would say that we can write this a couple of ways. We could write X I equals 1 to n, the product from I equals 1 to n of xi, or we could write it x1 cross out to xn, and that is the set of all ordered pairs. x1, I probably should have written some of this down here to give myself a little more room, but I guess we can squeeze this in, such that xi is in capital Xi, I equals 1 to n. Just kind of squeeze that in there on the screen. And so this is just the same idea, but for an arbitrary finite number of sets here. And sometimes you'll see this written this way because it's the idea that it's a product. So you'll see it sometimes written this way. I think this is a little better, probably. Either one's okay. I think people would pretty much know what you mean if you write it this way as well. So I think either thing is okay. So here, again, let me take these off so that what I write isn't right in front of my face here. Okay, let's also say that when x1 equals x2 equals out to xn, when the sets are really all the same set, and let's just say they're all the same set, capital X, we write this as, let me write it down here, I guess. We would write this is just capital X to the n, just what we've already done. And so here I want to, for the first time, I want to use a notion that I think is really valuable for us in understanding many things in mathematics, in economics, and this is a notion that I have never seen anyone else use. So you're not, to the best of my knowledge, you're not going to see this in any textbook. I'm the only person that I know of that uses this idea, but I find that it's extremely helpful. And that is, and let me introduce it by just taking a specific case here. So here we said, when all the sets are the same, and let's just say they're all capital X, we write x to the n. It's as if it's x to the n power, because it's like a product here. We write x to the n, and so an application of this statement right here is this statement that Rn is the set of all n tuples where each of these things is in R. So the way I describe this, and this is a kind of an elementary and maybe not the clearest, but it's the first, so I want to put it here, example of this, and that is that what's going on when I say, okay, we have this idea here, x to the n is the set of all n tuples where each of the x's is drawn from the same set x, and then I say R to the n, therefore, is the set of n tuples where they're all drawn from R. It's a situation where R, the set of real numbers, is now playing the role of the capital X down here. So you can think of it, and we'll see more examples and more detailed examples as we go along. But you can think of it here as that this is kind of the script, a very brief script, for a play or a television show or a movie. And in that script, it says, look, if you have a whole bunch of sets that are all the same set, and you want to look at the n tuples where the components are drawn from that set, you can write it as capital X to the n. That's a kind of a script. And then here, we're now saying, well, look, R, the real numbers, they can play the role of the capital X in this script. And when capital R, this R here, the real numbers, is playing the role of capital X, then R to the n will be playing the role of X to the n, so it will be the set of all n tuples where the X's are drawn from R. So I'm not going to belabor that now. I just want to mention it here because it's the first time where it kind of pops up and is useful. and it's not a big deal here, but we're going to see as we go along. This will be I think, a very powerful, useful way of thinking about things often. Now let's write down our definition of a function. So I'm going to write down a definition of a function from a set x to a set y. So we'll say a function for two sets x and y. And so we would say the function maps elements of x to elements of y, or the function is from x to y, so it's a function from x to y, or a function from x into y. So we have a lot of different related similar terminology because functions are so pervasive and they show up in different contexts. So we have a lot of similar but not identical terminology for this. So we have a function from the set x to the set y, and of course we all know pretty much what we mean by a function. It's a rule. It's a rule that tells us for every element of x how to assign the appropriate element of y to that element of x. So we would say y equals f of x. That would be the y that we get when we apply the rule defined by the function to an element of x. Well, that's kind of informal. It's kind of intuitive, but here we're going to give an actual formal definition of a function. So a function here for these two sets is a subset f of the Cartesian product, x cross y, but it's not any subset. It's a set that satisfies the condition, and of course you know already, presumably, that a function from a set x to set y can't assign different y's to the same x. For every x, there's only one y that goes along with that x. It could, the other direction, we could have multiple x's that go to the same y, but for a given y, for a given x, we can't have more than one y, so this has to satisfy the condition that for every x in capital X, there has to exist a y. Every x has to have a y that gets assigned to it. There exists one, but there exists only one. There exists a unique y in capital Y, such that you can say, wait a minute, how come I wrote it this way instead of the way we're used to writing it like this? And I wrote it this way because, of course, in this definition, f is a subset of x cross y. So f is a set, f is a subset. So it has elements, and the elements of f will be ordered pairs with an x and a y. And so writing it this way squares exactly with the idea that the function is a subset of the Cartesian product of x and y, and it is a subset that satisfies this condition. And of course, we write f of x equals y instead of, well, we sometimes do write this, but typically we write this instead of this. So that's going to be useful to have this formal definition. Even though it might seem at first a little bit awkward, it might be a little sort of more intuitive to just think of f as this rule that always assigns to every x a specific unique y. And of course that's what this definition says, but it says it a little more formally, and it'll be useful to have that. And in fact, let me, down here, let me give an example that we will come back and refer to. Let me see. Actually, let's put the example up here. So I'm going to take off some of the some of the writing up here, and we'll put a little simple example up here, I think. Okay, now I'm going to write down a really simple little example, finite sets x and y, and we'll actually use this example as a little bit as we move forward too. So this example is going to be one in which I have two sets, x and y. So x is going to consist of countries. I think I give a similar example to this in our earlier lecture. And I'll use the US, I'll use China, I'll use Mexico, and let's start off with just those three and let y, and in fact, let me call this h. H is going to be N and S. And so this stands for the United States. This is China. This is Mexico. This is the set of hemispheres. So, of course, I could have whatever. I have Eastern Hemisphere and Western Hemisphere. I don't know, but I'm only working with the Northern Hemisphere and the Southern Hemisphere here. So, so I'm going to actually write down the Cartesian product. So I'm going to use these lines to separate things out, and I'm going to have down here, I'm going to have U, C, and M. And there's no order to these. So when I write an axis like this for the real numbers, of course, 0 comes first, then comes 1 and 2, and so on. Here, this is just a place to put the elements of x. And so this is U, this is C, this is M, this is S, and this is N. I'll put N above S, north is above south. And so there are 6 elements of the Cartesian product, the ordered pairs consisting of a country and a hemisphere. So these are all the x's and y's, where x is in x and y is in h. So I intentionally used h instead of y just because I wanted to have another simple instance where I've got, in this case, capital H is playing the role of the capital Y in our definition of a Cartesian product. And of course, these are like playing the roles of the dummy variables, but I don't think that's probably a especially useful idea here. So I have 6 elements in the set, and in fact, let's even say this is x cross h, these 6 elements here. And so now let's look at the function that assigns to every country the hemisphere that it's in. Well, the United States is in the Northern Hemisphere, so I'm going to do a circle around the elements of x cross h that are in my function f. All right? Especially, let's even write that down. I'll write it in this color. Let's say f of x equals y means x is in hemisphere, I'll abbreviate that, y. And so here, China is in the Northern Hemisphere. Mexico is in the Northern Hemisphere. So this particular function is a constant function. I used some space here that I didn't want to use. I'm going to come back and use this. I'm going to take something off. So that's okay. So here, the function f is a constant function. It assigns to every element of capital X, it assigns the element n of the hemisphere set. So that's a constant function. Perfectly good function. Let's now do something more. So I'm actually going to take this off now. We know what f of x equals y means this. And so I'm going to take this off so I can use the space to do something here. So what I'm going to do here is I'm going to say this is capital X, and now I'm going to call it capital X1. And now I'm going to put another country in here. This is Australia. So now I'm going to refer to this as capital X2. And so now I want to look at my same function, but of course it can't be exactly the same function because now it's a subset of capital X2 cross H, but it's still going to be the function that assigns to every country the hemisphere that it's in, but of course Australia is in the southern hemisphere. So now my function is no longer a constant function. Some elements of x get n and some elements of x get s. And now I'm going to do one more thing. And that is I'm going to add in here the country Brazil. Let's also add in the country Kenya. Okay, so now x cross y has 12 elements in it, 6 times 2. And what hemisphere is Brazil in? Well, Brazil is in both hemispheres, partly in the southern hemisphere, partly in the northern hemisphere. Kenya, same thing, if I'm not mistaken. I haven't been to Kenya, so I only know this from looking at the map. So I believe Kenya spans parts of both hemispheres. So now what have I got? Let me call that, again, I took some of this space here, but I'll do this. Call that X3. And so now I want my F to be a subset of X3 cross H. And that F as a subset of X3 cross H is perfectly well defined. It's a perfectly good subset, but it's not a function any longer. It's not a function because to these two elements of X, X3 in this case, it assigns 2 different elements of H. So I'm going to leave this on because I'm going to come back and refer to this a couple of more times. It's real simple, and that's kind of helpful. The fact that it's simple is kind of a good thing here. So let's now go over here and let's lay out a number of sets associated with any function. So let's say that, let f be some function from a set x to a set y. And so what I'm going to lay out is basically some definitions. I'm not going to write definition each time, but they're definitions of some sets that are associated with f. So we have the domain of f is, which we write this way, is just the whole set x. So it's the set that f is defined on. Okay, so let's underline this because that's being defined. Then we have the target or target space of f is y. So we can think of f as kind of shooting an arrow from x over to y. And so y is the target space. F takes x's and sends them over here, and for every x, f takes that x and hits something in the target, hits a y in the target. Let's say the image of a subset, that's supposed to be an S here, a subset of the domain, the image of a set under the function f is the set f of s, that's the way we write it, and it is the set of all f of x's such that x is in capital X. We could write that another way as the set of all y's in y such that there exists an x in x such that f of x equals y. So two different ways, obviously saying the same thing. We have the domain, we have the target, we have the image, and now let's look at the range of f is just the image of the whole domain. So the range of f is all of the elements of y that get hit from some x in the domain. And last, we have the pre-image of a set. So we'll say the pre-image of a set V in the target space. The pre-image of a set V is written like inverse, and so it's like an inverse, but it's not literally the inverse typically. That's defined, and in fact I probably should put a little colon here just to emphasize this thing is being defined this way. Well, I did do that here, so we'll do that here too. So it's the set of all x's in x such that f of x is in the set V. Let's actually come back over to our simple little example and see what some of these things are in the two functions f1 and f2. And of course f3 is not a function, so we have to leave that aside here. But f1 and f2 are both functions with different domains. This domain is a subset of this domain. And so let's see what the domain, of course, the domain, in fact I just used that term, the domain of f1 is all of x1. It's the set consisting of the US, China, and Mexico. The domain of f2 consists of the US, China, Mexico, and Australia. The target space is the same in every case. It's the set H, that's the target space here, playing the role of Y in the definition. And so it's the two-element set H, that's the target set, the target space, we usually use that term. What's the image of a set in capital X? Well, let's take, for example, let's take the set S equals U and C, a subset of X2. So capital X2 has the four elements here, and if I just look at U and C, I have a set S that has two elements, and F of S is just the set consisting of N. So this is just the set consisting of N. So notice, this, as simple as it is, this is actually kind of a good example because it emphasizes that the image of a set is not a point. It's not an element. The image of a set is itself a set. The image of a set under F is a set. F of S is a set. And here it's a singleton set because the image set consists of only the one element. That's good. I mean, we could take a different S, but that looks fine. The range of, now the target space is the same for both functions f1 and f2. It's H. But the range of the two functions is different. The range of f1 is just the set consisting of only N. So let's just write that here. The range of F1 is the set consisting of just n. The range of F2 is all of h, because with F2, we actually pick up both n and s. And the preimage, what's the preimage? F1. What's the preimage of the set consisting of just n? The preimage of the set consisting of n, because the preimage is the preimage of a set in the target space. H is playing the role of y. That's a set. And the preimage of n under 1 is all three of these. They're all points in the domain that get mapped into n. And of course, the preimage of n in the function f2 still consists of the same three elements, because this doesn't get mapped to n, but it's not the whole domain any longer. Let's make this a 1. But the preimage of n under f2 consists also of u, c, and m, but that's not the whole domain, because now the domain includes Australia here. So this gives us some idea of what these sets are. And now let's look at a couple or three properties that a function might have. We say that f is onto the target space if for every y in the target space, there exists an x in the domain such that f of x equals y. So the function's onto if every element of y gets hit by the function f. And so, of course, coming back over here, f1 is not onto h, because s does not get hit by f. f2 is onto h, because both n and s get hit by the function f2. And so f1 is not onto, f2 is onto. We say f is 1-to-1 if f is 1-to-1 if an element of y only gets hit once, that there's only one x that goes to the y. So we would say f is 1-to-1 if for every y in, now it's not for every y in y, because some of the elements of y might not get hit. So it's for every y in the range, for every y in the range of f, there exists a unique x in x such that f of x equals y. Again, I want to emphasize it's not that for every y in the target space, because, for example, let's take, well, we actually don't have a function that's good. I have a function that's 1-to-1 here. But let's just point out that the function f2 defined on the 4-element domain is not 1-to-1, because there exist, in fact, 3 different points in the range for which there is not a unique x that maps to that. So for this one here, n, I don't have a unique x that maps to n. I've got 3 different x's that map to n. So neither of the two functions f1 or f2 is 1-to-1. We will see a couple of 1-to-1 functions in a few moments. So here's a bunch of definitions of sets associated with any function and potential properties of a function. Oh, there's one more thing I think I'll mention here, and that is that f is called a, and here I'll write it just this way, one-to-one correspondence between x and y if it is both one-to-one and onto. And we don't have that in our example, so we'll just have to wait and we'll see an example of a couple of examples, I believe, of one-to-one correspondences in a few moments. Tell you what, it's starting to go on a little long, so let's take a break here, and then we'll come back and we'll do several examples that will tell us something about these sets associated with a function and these various properties of sets. So let's do that, and then we'll come back and we'll do, as I said, we'll do several examples. Okay.